Hello and welcome to another session of Engineering Science and 3. My name is Sito Bejane. Today we'll be looking at electricity, which in most chapters this part is found in chapter 7, and it's mostly located on question 7 for your final examination. Now, electricity is a form of energy that powers up electronic devices. That could be your TV, that could be your microwave inside the household, but also electricity is used in manufacturing of other big materials like in industries. We use electricity today for trains. They are no longer using coal, but they use electricity. So electricity is a sophisticated phenomenon of a certain type of energy that we use. Now remember that is produced from a power station from the biggest power supplying company called ESCOM. But in today's session, we are not going to be looking at electricity generation or the usage of electricity in home appliances or industries. We are just going to be looking at how electricity is utilized in electronic circuits, how you are going to connect your circuit and how the electricity will be functioning in that circuit. How will the electricity behave when it meets a certain resistance? And how will that particular electricity changes in terms of voltage when you have connected your resistors either in series or in parallel? Now, we have two types of connections. Before we talk about the connections, in a certain circuit, we have the following components. We have a battery. This battery can be in a form of cells. Can be in a form of cells. We need to have resistors. Remember, before we talk about a resistor, a battery, that is a form of supply of energy, some sort of a power bank. But a battery is mostly identified as a DC supply. And if it's a DC supply, it means that's a direct current supply. It's not an alternating current. With a resistor, which in this case, this is a device to determine the amount of current or the voltage which is present in that particular circuit. Remember that the higher the resistance of a circuit, the lower the eligibility of conducting current in that particular circuit. So when we have the battery and resistors, these two must together utilize what we call voltage. The voltage and current are going to be utilized by the battery and resistor. The battery will produce voltage and current, whilst the resistors are the recipient of the two, the voltage and current. So when we talk about this battery that has cells, this is one cell. This is one cell. When you have cells connected all together, they form what we call a battery. So it depends on how you are connecting your cells. If you're connecting them in series or you're connecting them in parallel, that will produce a certain amount of voltage. But what we've learned from our previous level is that when you connect resistors or you connect cells in series, these types of cells or resistors will share the same current but different in voltage. When you connect them in parallel, they will share the same voltage but different in current. What does this mean now? Let us have a table here. In this table, we're going to have our cells connected in series. Let us have 1, 2, 3, 4 cells connected in series, namely E1, E2, E3, and E4. And we also have the very same cells connected in parallel on a different scenario. Namely E1, E2, E3, E4. Now, for us to get the total voltage present in this particular circuit, for a series, we are going to calculate the total EMF present in that particular circuit by adding all these cells. It will be E1, E2, E3, E4. If they are continuing, it's going to be En, depending on the number of cells you have. Or alternatively, you can just say E multiplied by N. Because in most cases, the voltage across the first cell will be equal to the voltage across the second cell, equal to the voltage across the number of cells present. So by simply multiplying the amount of voltage present in each cell and multiplying it by the number of cells, you get the total EMF present in that particular circuit. This means that the voltage present in a series connection is not the same. Hence why we are adding these EMFs. But if you have voltages or cells connected in parallel, like this one in our second scenario, remember, parallel connection, we share the same voltage but different in current. What does this mean now? It means that the total EMF present in that particular circuit will be equal to E1, equal to E2, equal to E3, and if you have many, it will be equal to En. This means that if E1 was 1 volt, then E2 1 volt, E3 1 volt, E4 1 volt. Therefore, EMF will be equal to 1 volt. But if here we had E1 being 1 volt, and we have 4 number of voltages, we're going to say 1 volt multiplied by 4, which we get the total of 4 volts. I hope you are understanding that. Now, let us talk about resistors. We have two types of resistors when it comes to this circuit. We have an internal resistor and we have an external resistor. An internal resistor is that resistance which is obtained inside a cell of a battery. This means that each and every cell in a battery consists of an EMF and an internal resistance indicated with a small letter R. We are not going to be looking at the external resistance just for now, but as we go on, we are going to be looking at the external resistance. However, an external resistance is indicated by a capital letter R. Now, let us say now E1 has an internal resistance R1, R2, R3, and R4. Same applies here. You have R1, R2, R3, and R4. The laws of Ohm state that, as we spoke, series connection we share the same current but different in voltage. This means that if I were to calculate the total internal resistance in this particular circuit, total internal resistance, I'm going to put a small r with the capital letter T for total. This is going to be equal to R1 plus R2 plus R3 plus R4, depending on the number of cells you have. Or alternatively, you can just say R multiplied by N. N for the number of cells present in that particular circuit. R for the resistance present in each cell. There are very few cases where the value of R1 will be different from the value of R2, different from the value of R3, and so forth. Normally, the value of R1 and E1 will be the same as that of cell 2, cell 3, cell 4, and so forth. But what happens when you've connected them in parallel? Does it mean that the total internal resistance is the same as R1, the same as R2, the same as R3? No. In this case, the total internal resistance is calculated as 1 over RT is equal to 1 over R1, 1 over R2, 1 over R3, and so forth, depending on the number of resistance that you have. Unfortunately, with the parallel, there's no shortcut just like the series one. You have to add them in that fashion. And then you use your mathematics knowledge to calculate the total resistance present then. Now, in the case where you are having these circuits or these power sources connected to a supply where there's an external resistor R. Remember, good people, R represents the external resistor. I will represent the current present in that particular circuit. V will represent the voltage present in that circuit. Normally, they will use E for EMF, and then small r is for internal resistance. Now, if you have all these connected in one circuit, your equation should be given as E is equal to I into R plus R. E being the total voltage present or the total EMF present in that particular circuit. I being the current which is supplied to the two resistors, the external resistor and the internal resistance. Now, with all that being said, let us take this now and move to an example. Example 1 reads as follows. 4 cells, which each has an EMF of 1.5 volts and an internal resistance of 0.4 ohms, are connected in series. Two resistors of 6 ohms and 8 ohms respectively are first connected in parallel, then connected across the terminals of the battery. To make things easier here, we need to sketch. After we've sketched that, it will be easier for us to calculate exactly what they are looking for. Now let us sketch this circuit here. First, I'm going to sketch my resistors which are connected in parallel. These are my two resistors, external resistors, which are connected in parallel, 6 ohms and 8 ohms respectively. They said first are connected in parallel, then across 4 cells. 1, 2, 3, 4 cells, with each having an EMF of 1.5 volts, 1.5 volts, and so forth, and an internal resistance of 0.4 ohms, respectively. Now, this is our circuit. The first question, number A, they want us to calculate the current through each cell. The question wants us to calculate the current through each cell. Now, remember, we had the equation that side, which is EMF is equal to I into R plus R. But what is the first thing that we must calculate here in order for us to calculate the current through each cell? Firstly, let us calculate the total EMF. Total EMF is going to be given by E multiplied by N. This is going to be 1.5 volts multiplied by 4. We have how many cells? We have 4 cells. Now you take out your calculator, you type in 1.5 multiplied by 4, and you get 6 volts. That is the total voltage present in that particular battery. We also need to calculate our total internal resistance, R multiplied by N, and our resistance is 0.4 multiplied by 4. And this should gives us what? 0.4 multiplied by 4. The total internal resistance is 1.6 ohms. We're going to then move on and calculate our total external resistance. Since we have two resistors, we can use the equation R is equal to R1, R2, R1 plus R2. Or Alternatively, you can say 1 over R is equal to 1 over R1 plus 1 over R2. Since they are connected in parallel, it's still very much acceptable. It's going to be 6 times 8, 6 plus 8. This side it's going to be 1 over 6, 1 over 8. So when I punch on my calculator, 6 times 8, 6, 6 plus 8. This gives me 3.429. 3.429 ohms. You can then work this out, but because of time, I can't work that out because we need to move to the finish line. Now we've calculated the total external resistance, the total internal resistance, and the total voltage present in that particular cell. We can then now move to our equation. E is equal to, let me write that in a red. E is equal to I into R plus R. We're looking for what? We're looking for the current in that particular circuit. It's going to be equal to E over R plus R. This is going to give us what? It's going to give us 6 all over 3.429 plus 1.6. Punch that in our calculator. 6 over 3.429 plus 1.6. This gives us 1.193. 1.193 amperes. This is the current which is present in that particular circuit. Now the next question says calculate the terminal voltage of the battery. That is number B. Perhaps we did not talk about this, but let me try and elaborate on that one. When we talk about a terminal voltage, let me raise this one so that we can have adequate space. We have 3 types of voltages that you need to understand. The first one is the EMF. EMF means electromotive force. This is the voltage which is present in a power source before the load is connected or when the switch is open. Now, this voltage, normally when you are going to buy your battery, you will find it written outside your power source. It can be 1.5 volts. That is EMF because at that particular moment, that voltage is not yet connected. We have what we call the terminal voltage. I'll write it as TV. Terminal voltage, it is what you are going to collect from the terminals of the battery when the switch is closed or when the circuit is connected to the load. It means that the terminal voltage is not equal to the EMF. It will always be less than the EMF. Why? Because the moment you connect your power source to the load, those cells inside are going to have a share of their voltage, which means that we're going to have an internal volt drop. And that internal volt drop is called the potential difference, PD. Now, EMF is equal to the terminal voltage plus potential difference, which means that for you to find the terminal voltage in that particular voltage source, your terminal voltage, not I, your terminal voltage will be equal to your EMF minus your potential difference. What is your potential difference? The potential difference is the current multiplied by the internal resistance in that particular circuit. So number B, we're going to say V is equal to EMF minus I times R, which is the terminal voltage. 6 minus 1.193 multiplied by 1.6. This is how we calculate our terminal voltage. 6 minus 1.193 multiplied by 1.6. This gives us what? 4.091. 4.091 volts. Look at this. Look at the difference of 4 and 6. Can you see that? Originally, when the switch is open, the EMF was 6 here. But the moment the switch is closed, the voltage goes down to 4. What happened to the rest? It went to the internal resistance of the power source. Let us look at number C, the current through each resistor. Which resistor? The external resistance. These resistors, we need the current through these two resistors. Remember, when the resistors are connected in parallel, they are not going to share the same current. We're going to have I1 and I2, but they will share the same voltage, which is the 4.091 volts. So to calculate the current through the first resistor, it will be the voltage, divided by the resistance, which is 4.091 divided by 6, and then to calculate I2, it will be V over R, which is equal to 4.091 divided by 8. So let us punch that in our calculator. 4.091 divided by 6. This gives us 0.682. 0.682 amperes. And then the other one will give us what? 4.091 divided by 8, we are going to get 0.511. 0.511 amps. I hope you're following, you guys. Now the last question, number D, says calculate the internal volt drop. The internal volt drop, what is the internal volt drop? It's the potential difference. The potential difference between the EMF and the terminal voltage will be given by I times R, which is 1.193 multiplied by 1.6. Now we are calculating that value. 1.193 multiplied by 1.6. This will give us 1.91. 1.91 volts. I hope everything is clear and there's no blur in what we're doing here. This is basically how we would calculate our resistors, more particularly when your EMF is connected in series. Now, I want you to go and look at this question here. This is the question that you'll be doing on your own, and you're going to try to calculate whatever equations they are given to you. They say a circuit consists of 4 cells, each with an EMF of 1.5 volts, connected in series. Each cell has an internal resistance of 0.5 ohms. Two resistors of 3 ohms and 6 ohms are connected in parallel to the circuit. The battery is now connected in series with a radio of 4 ohms and a loudspeaker of 2 ohms. Now, take the radio to be a resistance still, and take the loudspeaker to be a resistance still. This is the trick that you only find in this question. Calculate the total resistance of the circuit, the current flow in the circuit, and the volt drop across the loudspeaker. On our next session, we are going to be discussing this question, and then we'll also discuss further other questions with which you might have during the lesson. That's it for today. We will continue with our electricity when we are dealing with other aspects of electricity. My name is Sito Bejane, and this was TVET Clinic.